Welcome back to Applied Physics Lecture Series, Unit 4, Fiber Optics, Lecture 10, Losses in Optical Fibers. So during the propagation of light signal in the core region of the optical fiber by undergoing total internal reflection, so usually some type of losses, specifically known as transmission losses, are arised in the optical fibers. Let us see what are those transmission losses and how you will define these losses in case of optical fibers. When the when light signal propagates through the fiber, it suffers a loss of amplitude and change in shape. The loss of amplitude is called as attenuation and change in shape is called as distortion. So usually when light transmits to the optical fiber, it suffers with the two major changes. One is there is a change in the amplitude. So as a result, loss of amplitude is known as attenuation. And if there is a change in shape, that will be called as distortion. Attenuation, the loss of optical fiber as light travels down a fiber is known as attenuation. And in terms of optical fiber terminology, attenuation is more specifically defined as it is the ratio of input optical power into the optical fiber to the power of light coming out at the output end of the optical fiber. So optical power input is represented with Pi and optical power at the output end is represented with P naught. Therefore, attenuation coefficient, which is represented with alpha, is represented as 10 by L into log Pi by P naught base 10 decibels per kilometer. Here L is length of the fiber, Pi is the input power and P naught is the output power and decibel is the unit to represent transmission loss. Attenuation mainly arises due to absorption, scattering and bending. Now let us see all these three in detail. So first one is due to absorption loss. In the glass fibers, three different absorptions takes place. So first one is ultraviolet absorption. Absorption of ultraviolet radiation around 0.14 micrometers results in the ionization of valence electrons. As a result, absorption takes place. And second kind of absorption is infrared absorption. Absorption of infrared photons by atoms within the glass molecules causes heating. As a result, it will produce an absorption peak at 8 micrometers. Also minor peaks at 3.2, 3.8 and 4.4 micrometers. Third type of absorption is due to ion resonance or OH absorption. The OH ions of water trapped during the manufacturing causes absorption at 0.95, 1.25 and 1.39 micrometers. As a result of these three, mainly absorption losses arise. Second type of loss is scattering loss. The molten glass, when it is converted into the thin fiber under proper tension, creates submicroscopic variations in the density of a glass. Dopants, usually which are used to change the refractive index, cause inhomogeneity and present act as scattering centers in the fiber. This lead to the losses. And another way is nothing but this is also known as Rayleigh scattering and depends upon the wavelength of the light. So scattering losses are inversely proportional to the fourth power of the wavelength. Wavelength below 800 nanometers have high Rayleigh scattering losses and wavelength above 1700 nanometers have high losses due to infrared absorption. And if you notice the graph or the diagram which is showing all the losses, here attenuation, transmission losses taken on the y-axis and wavelength is taken on x-axis. You will notice Rayleigh scattering, high Rayleigh scattering, low Rayleigh scattering, infrared absorption tail, OH scattering, ultraviolet absorption scattering, all those are represented here. And another type of loss is nothing but bending loss. So wavefront travels perpendicular to the direction of propagation. So for this, the part of the mode outside the bend has to travel faster than inside. But according to the Einstein's theory of relativity, in a single wavefront, one part should not travel with high velocity than the other part. So all the parts must have maintained the uniform velocity. So the part of wavefront traveling in cladding medium lost in the form of radiation leads to the bending loss. You will notice this one, cladding and wavefronts which are lost in the form of radiation. And another type of losses, micro bend and macro bendings. So micro bend is a small scale distortion. So this is due to change of shape. So change of shape leads to distortion. So here the distortion losses are microband distortion and macroband distortion. Microband is a small scale distortion. It indicates pressure on the optical fiber. We can able to see such a small bend on the left hand side of this diagram. Macrobending is a large scale bend. When a fiber is bent through a large angle, it undergoes a strain. The bending strain will affect the refractive index of the material and the critical angle of the fiber in that area. So that leads to losses. So the macro bend, so large bending. So we'll see in the right hand side portion of the diagram. Coming to the distortion, the short form, the light pulse transmitted through a fiber are given width of amplitude and interval. Given width, time, amplitude, and interval. These light pulses broaden and spread into a wider time interval because of the different times taken by the different rays propagating through the fiber. This phenomena is known as distortion or pulse dispersion. It is expressed in terms of nanoseconds per kilometer. Thanks for watching.